Hello, this is Marco Tita from StreamSim Technologies, and this talk is about the myths of fixed well patterns. Possibly the most reproduced pattern picture is that given by Forrest Craig in his 1971 SPE monograph, The Reservoir Engineering Aspects of Water Flooding. In this classic picture, triangles indicate injectors and open dots indicate producers. Regular patterns have the producer in the middle, while inverted patterns have the injector in the middle. Implicit in these patterns is that the dashed lines represent the pattern boundary, and that volumes produced from or injected into a pattern do not cross these boundaries. And most importantly, these patterns are assumed to be fixed in time. In the case of irregular well locations, reservoir engineers still try to define patterns by drawing pattern boundaries using polygons, as shown in the picture on the right. However, this becomes increasingly difficult and tedious as the number of wells increase, change with time, deviate, and produce from different vertical zones. The need to define patterns comes from the desire to extract two flood performance metrics. One, a per pattern recovery factor to quantify the local sweep efficiency and the amount of remaining oil in the pattern. And two, a per pattern volume replacement ratio to quantify the pressure support in each pattern, as well as the extent of over or under injection into the pattern. But both metrics rely on a good estimate of volumes injected into or produced from the pattern, as well as the pattern volume itself. Before addressing the myths of fixed patterns, it is worth asking what is the best way to associate well pairs to each other. The answer is using streamlines. Streamlines represent the most accurate approach to quantify relationships between wells, and they can be collapsed into a flux pattern map to express a per injector or per producer pattern. Streamlines are traced using a numerical model that computes the total velocity at a given time using well rates, well locations, well perforations, fluid properties, and grid properties as input, schematically indicated by the left picture. This is equivalent to solving for pressure in a reservoir simulator. In the middle picture, the green streamlines represent flow from the central injector to the various offset producers at a particular moment in time using the calculated velocity field. The green streamlines connecting an injector-producer pair can then be collapsed into an edge, where the thickness of the edge represents the fraction of flow from the injector to each producer in the pattern. We call this fraction the well rate allocation factor. The flux pattern map in the right picture represents an inverted pattern with offset producers, including the well allocation factors at a particular moment in time. And this brings us to myth number one, that patterns are fixed. Patterns must be changing through time because wells are opened, closed, infill drilled, and converted over time, and well rates also change through time and across the field. In this example of a single injector displayed using the flux pattern map, the inverted pattern changes through time resulting from the changing flow field, or streamlines. Patterns are not fixed but instead change dynamically through time as the flow field changes in response to changing conditions at the wells. Myth number two is that one can compute the volumes, including the oil volume, in and out of a pattern, as both the recovery factor and the voidage replacement ratio require knowledge of these volumes. Drawing any box around an injector, either the black rectangle or the red polygon, automatically implies which wells are supported by the injector. To compute volumes in and out of a fixed pattern, one then has to ignore the efflux or influx across the pattern boundaries. But for the black pattern on January 2018, this would mean ignoring 11% of the injected volume flowing out of the pattern to P1, as that well is not included in the pattern. Two, assume that production from the pattern is only due to wells assigned to the pattern. But in the case of the red pattern, This would include wells P2, P3, P4, and P5, which should not be contributing to the pattern production, as we know from the streamlines. And 3, we still need to assign production allocation factors to pattern producers. So regardless of how the pattern boundaries are drawn, it is not possible to reliably calculate the volumes in and out of a fixed pattern needed to calculate the recovery factor or the voidage replacement ratio through time. Myth number 3 is that the original oil in place of a fixed pattern is known. The recovery factor of a pattern requires the OOIP of a pattern, but this number is rarely known. 1, patterns are not established at time equals 0 when the original oil in place map of the field is estimated possibly from an equilibrium condition calculation. And 2, patterns are established over time and possibly much later. Thus, at the moment a pattern is defined requires knowledge of the oil in place map of the field at that time. So this would require a detailed time-varying oil in place map of the field, which is generally unavailable. In summary then, fixed well patterns rely on 3 myths that need to be dispelled. As 1, patterns are not fixed, as we know from the streamlines. 2, the volumes in and out of a pattern cannot be reliably calculated. And 3, the original oil in place of a fixed pattern is generally unknown, meaning that computing the recovery factor and the voidage replacement ratio for fixed patterns is a guessing game at best. A sounder approach is to define patterns using streamlines, calculated from the historical production and injection rate data, and thereby accounting for the dynamic nature of any production strategy. Thank you for listening. I'm Marco Thiele. If you have any questions, please visit us at streamsim.com or email us at support@streamsim.com.